This camera's sensor is a single pixel, but it can take photos with thousands of times more resolution than it should be able to. That singular sensor can take photos like this. And with some recent upgrades, it can even take photos in color. But first, let's go all the way back to before I made those changes. Let's go over my first camera. The video on it has more detail, and you can check that out right here. But essentially, it works by using a lens to focus the light and then moving a photo transistor to the location of each pixel in the photo to test how bright the light is. By doing this hundreds or thousands of times, we end up with a photo just like an ordinary camera. Unfortunately, this can be a very slow process. After over 4 hours of filming, this 100 by 100 pixel photo was the most detail it could capture. The biggest factor slowing the camera down is EMI. That stands for electromagnetic interference. EMI can occur when many electrons change direction very quickly, like they do in the coils of the stepper motors. This can cause electrons to flow in nearby conductors, like the wires connected to the phototransistor, resulting in incorrect pixel measurements for our camera. Here, I have a phototransistor and stepper motor. This oscilloscope feed shows the light reading emitting from the phototransistor. As you can see, when the motor's turned on, interference from the coils in the motor completely drown out the reading. In my last video, I turned the motors off before taking a measurement, but that solution came with some problems. We can turn them off, take a pixel, and then turn them back on when we need to move. But this makes a new problem. If you look closely, you'll see that every time the motor turns back on, it jumps a little. This may not seem like a big deal, but over time, this error will add up to make it impossible to know where the pixel sensor is. I got around this by recalibrating the pixel's position after every measurement. But that extra movement takes up a lot of time, hours or even days for a high-resolution photo. This time, I needed to fix the EMI, not just find a workaround for it. EMI is commonly fixed with metal shielding, so I used a sheet of aluminum placed between the phototransistor and the stepper motor to try to reduce the EMI. When I turned on the stepper motor, you can see that it substantially reduced the EMI. I was talking with a friend about this project when he suggested that I ground the aluminum for even better EMI protection. Sure enough, when I grounded it, it reduced the EMI even further. After a bit of CAD work, I came up with a metal casing for the stepper motors to reduce the EMI. I was about to send it off to be made, but something felt off. Grounded metal. Metal shielding reduces EMI. Where am I? What's going on? Ground the metal. Help. Am I spinning? Am I spinning this time? Ground the metal. The stepper motors are metal. I decided to try grounding the stepper motor in case it fixed my problem, and sure enough, it significantly reduced the noise. Now that I've learned, I won't be making that mistake again anytime soon. I made a bunch of small changes, but I'm gonna go rapid fire so we can get to the good stuff. I soldered ground wires to these washers, then attached them to the stepper motors to let me keep them grounded all the time. The EMI was still not completely gone, so I designed and ordered custom PCBs for signal amplification to reduce the EMI even further. Then, I redesigned the pixel carrier to allow me to move the amplification PCBs around with the light sensor. My gears were wearing out really quickly, I think because the motors were too hot. So, I designed mounts for these tiny fans to cool them down. I noticed the camera was having trouble focusing on close-up targets, which I confirmed using this wax paper at the same distance as the light sensor, so I moved the lens further from the camera to allow a better range of focus distances. Sure enough, this really improved the clarity of the image. I noticed the pixel movement wasn't very accurate, so I rewrote the code to let it smoothly accelerate to improve the accuracy. Then, I noticed it was wasting a lot of time moving only one motor at a time, so I rewrote the code again to allow it to control both motors at once. I wasted a ton of time relying on the changing colors of this LED to find bugs in my code, so I rewrote the code again to let it send me detailed errors when things go wrong. I think I can still tune it a bit, but I'm already taking better photos due to these changes. This 32 by 32 photo used to take me 3 minutes, but now it only takes 45 seconds. And this 512 by 512 photo took only 40 minutes, but is by far the best photo I've ever taken with this camera. Now, it's time for the biggest change yet, the jump from black and white to color. The photo transistor I'm using picks up a wide spectrum of colors, so I need a way to isolate the red, green, and blue channels that make up a color image. Luckily, I have just the thing. By putting these colored plastic sheets in front of the camera, I can isolate each color. Then if I combine 3 separate photos together, I can get a color image. For reference, here's what it actually looked like. This process is very time consuming though. I have to take the red photo, switch to the green filter, take another photo, switch to the blue, take one more, then combine them all together at the end. It'd be better if I could automate it so the camera can take the color photos on its own. I cut the plastic into thirds of a circle, then glued them onto a 3D printed wheel. If I spin this wheel in front of the camera, I can change which color it sees. But how does the camera know which color is in front of it? I designed cutouts in the wheel, 2 for red, 1 on the outside for green, 1 on the inside for blue, and nothing for areas where the color transitions. I glued in some LEDs and light sensors, and I can use these sensors to determine what color is in front of the camera at any given moment. As it spins, you can see the combinations for red, green, and blue filters that the sensors will pick up each rotation. With that out of the way, I set up for my very first color photo and hit start. Okay, after fixing some wires that were plugged in backwards, I started it up. Now, for the first automatic color photo. I tried multiple times without any good results. Then I realized why the problem seemed so familiar.
I won't be making that mistake again anytime soon.
I've already seen this before. It's EMI troubles. After grounding the additional motor, I tried again, and well, it's not perfect, but it works. I tweaked it a bunch of times, and here's some of the photos I took. There's still a number of limitations with this setup. I can't seem to get rid of the blur as I go to higher resolutions. I think the size of the sensor is to blame, but I can't be sure without testing with a smaller sensor. And even if it were clear at higher resolutions, filtering out some of the colors means I have to sample longer to get rid of the noise. And the camera shakes so much at higher speeds, I don't think I could even get anything of value out of it. Despite its many flaws, I wanted to see what its photos outside would look like. So I packed it up, lugged it up to the roof, and took one final photo. And here it is. Okay, it's clear the sun was a little too bright, so I took another photo of a tree on my roof, and you can see that here. Overall, I'm really happy with how this project turned out. And if you're happy here, make sure to like, subscribe, and comment to let the algorithm know you like my stuff. If you want to see more from me, check out my first video on this camera. Thanks for watching.